Okay, on to our next question. We are looking for the difference between polar protic and polar aprotic molecules, and it all lies within hydrogen bonding. So in polar protic, we tend to have hydrogen bonded to a highly electronegative atom. And if we just look at the periodic table, so the structure of the periodic table is very beautiful in my opinion. Um, because you have trends across the groups and the periods that you of course learn about in high school, and we have electronegativity increasing this way and this way, which means fluorine is our most electronegative, oxygen is also highly electronegative, and nitrogen is also highly electronegative. And so in the case where hydrogen is attached to oxygen, fluorine, or nitrogen, what happens, let's just write that down here. So it needs to be oxygen, nitrogen, or fluorine in most cases, and nearly all cases that you'll deal with. And the reasoning is because their electronegativity is so high that it virtually almost pulls the entire electron from hydrogen, which leaves an extremely polar molecule left behind. So let's take the example of H2O. So what happens is that because this pulls the electron from them both, it leaves them with a slightly, a slightly positive charge, a slightly negative charge, and a slightly positive charge, but more so than you would have in a polar aprotic, where the atom isn't as electronegative, so it doesn't pull the charge away as much and doesn't cause as strong partial charges. And this is actually the reason why water is such a good solute and is so good at dissolving other things. And it's because of the fact that what happens is, like, let's say we have a positive ion and a negative ion together, like lithium bromide. What happens when you put it in water is because of oxygen's now more than usual negative charge, it's going to be pulled to the positive ion and surround it. So oxygen will be closest and it'll form sort of a shell, completely isolating it from the other one, basically splitting the two away from each other. And that's how you have things dissolve. Yeah. And you're going to have the same thing occur with the negative charge, except now the hydrogen will be strongly attracted to it. So you're going to have a negative charge. Let me just put them in blue. Surrounded by, oh, let's just write down and so that's why water is so good at dissolving things, because it basically attacks it, splits them, and surrounds them, which would prevent them from coming together again. Now, polar aprotic is still polar, so hydrogen is still attached to an atom that is more electronegative than it, but not as highly electronegative as oxygen, nitrogen, and fluorine. So it's still polar, it just doesn't have the capability of hydrogen bonding, which doesn't allow it to do all of these special tricks that water does. And a good example of this is actually in our organic compounds, where we have hydrogen attached to carbon. And so let's take the example of acetone. So yes, hydrogen will still have a partial positive charge, and carbon will have a partial negative charge, but not strong enough that it would lead to characteristics like this. Just it would be slightly weak and rely on other interactions like dipole interactions and van der Waals forces in order for things to happen in reactions.